All the way blue. Oh, we are live, homie. We are live. Boom. Now I can hear myself echo. We don't want that. We want this right here. All right, so what's up, party people? It's Mr. Harris, and we are on for my first of all, appreciate you for watching this live. If you're watching this live, if you're one of my students or not, thank you so much. Remember to like, share, and subscribe. All right. So let's get to it. We are in Unit 5, Lesson 13. Remember, Unit 5, for those of you that are watching this, it's about functions, inputs, outputs, independent values, dependent values, those kind of things, right? And so in this particular lesson, we're talking about inputs and outputs that don't make sense, okay? So let's get to it. For the students, I want you to go over in your Unit 5 workbook. We're starting with Activity 1. Going to page 131, I'm going to share my screen. And as you can see, I have a presentation. It's got a little bit of color in it now. I'm tired of using them bland slides, inputs and outputs that don't make sense. And we're going to Activity 1 on page 131. It says, well, I will assign you some scenarios to work on. But notice, let's get straight to the question. For each pair of values, which one makes the most sense as the input? And when possible, include a reasonable unit, okay? So part A says the number of popcorn kernels left unpopped as a function of time. Now, when you see this term right here, as a function of, boom, as a function of, okay? So watch this. Number of popcorn kernels, that is going to be your dependent. I don't like this wide line, okay? So let's make that a little thinner. So that's the dependent variable or output. And as a function of, this is going to be your independent variable. Independent. Sometimes I can't spell. So output, okay? So notice, key thing is, so if we go back to basic function notation, this says f of x. So a little helpful hint is when you say f of whatever comes after of is your input, okay? So in this case, if I was to name this, well, I don't want to name it because it's popcorn kernels. We could, popcorn is p. So we could say, since it's a function of time, p of t. So since the t, which represents time, comes after the of, that is the input. I'm sorry, I did that wrong. Look at that. Players mess up too. I'm sorry. My bad. I didn't write that on purpose. This is input. I'm sorry. Listen, unedited, live. I'm going to tell you when I make a mistake because I am cool with that. All right, so this is the input. All right, does it make sense? The number of kernels left unpopped, if you pop popcorn in a bag, the longer you pop the popcorn, the less kernels of popcorn that go unpopped. Now, I have never seen a bag of popcorn that has any kernels unpopped. But to stay on topic, the input is the time, okay? So the more time you cook the bag of popcorn, the less kernels that are unpopped, all right? I hope that makes sense, even with the mistake. Let's look at part G. The cost of crab legs as a function of weight, all right, of the crab legs. Okay, remember, so let's just say crab legs. Let's go with C of W. W for weight. C for crab legs, or C for cost. And then W as weight. Okay, now, if you're a seafood lover like I am, you know the more seafood that you order, typically seafood is purchased by the pound. So the cost is determined by the weight. Okay, so here our input, so cost of the crab legs is going to be our output, and weight of, we're just going to say weight of the crab legs is our input. Okay, how can we relate this to real life? You want to know, does the weight of the crab legs determine the cost, or does the cost determine the weight? Okay, So if you go into a grocery store right now and you order some crab legs, they're going to take them out and they're going to put them on the scale, okay? And you're going to see a scale that tells you the weight, and the cost is going to be determined by the weight. There's usually a unit price per pound. So that's that. All right. So let's go on to the next. All right. So for each pair of variables, which one makes the most sense as input? When possible, include a reasonable unit. Well, guess what? Let's look at these. This is a little different. This is given as a graph. All right. Boom. Your input is typically on your x-axis. So input. Boom. And your output is usually on your y-axis. So output. Now, let's see, does this make sense? Is the price of a rental van determined by the miles driven? In a lot of cases, if you go rent a car, right, you have a price per day. Now, sometimes they charge you by the mileage, sometimes they charge you by the day. But in this case, because they talk about the miles driven, the proper input, it does make sense for the miles driven to be the proper input. Okay. Sometimes they'll tell you a price per day and you have a maximum amount of miles that you can drive. But in this case, yes, the way this graph is drawn, the input of distance driven in miles, so the number of miles you drive, does determine the price. All right. Over here to the next one. We have time in seconds. We have the height of an elevator in meters. If you're not scared of elevators, because a lot of people don't like going on elevators. They're afraid of heights. Maybe they're scared of getting stuck in one, whatever. I don't know. But in this case, the height of the elevator, is it determined by the time in seconds? It absolutely is. Okay, so the input would be the time. The output would be the height, whether it's going up or down. So let's say let's say I get on the elevator on a 10-story elevator. Let's say I get on it on the 3rd floor. Okay. The height of it is determined by the time I'm on the elevator, because when I first enter the elevator, the time is at 0. So like, for example, in this case, when I first get on the elevator, we were at 600 meters. Okay. And as you can see, as the time goes on, this elevator is going down. Okay. So the input would be the time, the output would be the height of the elevator. And if you old school like me, you know about the old school commercial, cartoon where they said elevator go up, elevator go down. I'm showing my age a little bit, but it's okay. Number 2, write an equation or draw the graph of a function relating the two variables. For this one, I'm going to basically just look at this. I'm not going to draw any graphs, but I want you to look. Part A says it gives you the input is the side length of a square. Okay. So it's the side length of a square. All right. So input is side length of a square. The output is the perimeter of the square. Now we know that squares have all 4 sides that are the same. Excuse me. So if we determine the perimeter based upon the side lengths, we can write this as P of S. P being perimeter, S of side length. So yes, this we could say P of S. So that would be the equation. That would be the equation. And now, how do you find the perimeter of a square? You take 4 times the length of each side. So that would be the equation. That is 4S, not 45. Okay. So P of S, the perimeter of a square, is based upon the side lengths. Okay. So once again, input, output. All right. So for example, if I say, let's say what is the perimeter of a square that has sides that are 5? All right. So 4 times 5. Well, P of 5 equals 4 times 5 is 20. Okay. And B, let's change the color up. The input time spent walking in minutes. the output, the distance walked in meters. Okay. So the distance you walked is based on the time that you've been walking, right? Yes, you're right. All right. So we can say D, distance, is a function of time. Okay. So if distance is a function of time, let's just say, so distance is a function of time. So now we don't have a formula for this. Okay. So we could simply just say D of T, but we could draw, I said I wasn't going to draw no graph, but we could draw a graph. All right. So we can say time, and we can say distance, and, oh, that's not cute. All right. So what we can say with this is that you start out at 0, 0 because the time is 0, and it just goes up. Now, it may go up at a different rate depending on whether you're walking or running and things like that, but that it would be a graph that you could put with that. So the input is time, the distance is the output. All right. Let's look at the last one. Input, time spent working out in minutes, and the output is the heart rate in beats per minute. Okay. So this one, once again, we could say R for rate and T for time. Now, we don't have anything to set this equal to because there's no formula to find out how fast your heart speeds up or how to measure your heart rate, but we can draw a graph of this. And in this case, we would put time on the input, and let's put heart rate on the output. Okay. So the longer you work out, the higher your heart rate. Now, sometimes it may go down. If you go from running to walking, it may go down. Okay. It could go up and down, things like that. But the heart rate is a function of the time spent working out. It can increase and decrease depending on what kind of activity you're doing. Sometimes it may start low, sometimes it may go high, but it rarely stays the same unless you stop and you just be still. So it can get to a point to where it's just boom, like that. All right. But as long as you're working out, your heart rate is going to be going. All right. I think we have another activity on this. We do. We have an activity 2, which is on page 133. All right. So I'm probably going to do more talking on this one. Wait, hold up. Something wrong. Wait. Oh, no, I'm still right. Okay, cool. This is out of order. Okay. So I apologize. This is still activity 1. It's out of order, but it's okay. So we're at the top of page 132, but it's all good. For each pair of values, which one makes the most sense as the input? When possible, include a reason. F of t equals 5t plus 8, where t represents the time that a bike is rented in hours, and F of t is the cost of renting the bike. Okay. So the time makes more sense as the input. Okay. Time makes more sense as the input because the cost, if you're renting a bike, it's gonna cost you more time. If I rent the bike for 1 hour and you rent the bike for 5 hours, you're gonna probably pay more money. Okay. And in the next one, F, G of n equals 7n plus 4, where n represents the number of pencils in a box and G of n represents the weight of the box of pencils in grams. The more pencils in the box, n is going to determine the weight. Okay. So if I have 5 pencils in a box, it's going to weigh less than a box if I have 12 pencils in the box. Okay. So this is just a little explanation. Nothing really to write here. We could find out, well, what is the weight of the box if there are 5 pencils in it? And then we could also compare that with the weight of the box if there are 7 pencils in it. So you just can determine any value of n that you want. Okay, so G of 5, let's just write it. Come on, let's write something. So basically, if I say, well, what is the weight of the box in grams if there are 5 pencils in the box? Then you would say 7 times 5 plus 4. Okay, so G of 5 equals, we got to multiply first. 7 times 5 is 35 plus 4. So the weight in grams of the box of 5 pencils is 39 grams. Well, let's use that 12. Let's say, what do we want to know? What if we want to know the weight of the box in grams if there are 12 pencils in it? So 7 times 12 plus 4. G of 12 is equal to 7 times 12, I believe, is 84. And then plus 4. So the weight of the box in grams, if there were 12 pencils, would be 88 grams. All right. So, although I kind of misplaced the slides, that's okay. Go on to the last one. Activity 2. Now, activity 2, not much explaining, but there is some explaining. Okay, so I'm gonna write on this one a little bit. It says, what's wrong with these graphs? The graph relates the length of a side for a square and the area of the square. So we notice the input is the length of the square, or side length of a square, and the output is the area of the square. Notice this has 4 quadrants, okay? So what this is saying is, boom, when the length of the side of a square is -2, it has an area of 4. But can you have a negative length? Absolutely not. So even though when I have a negative, if you could actually have a negative length and it was -2, the output would be positive. But anything when the side length is less than 0, actually, if it's 0 or less, then this does not make sense. It's not possible because length cannot be negative, okay? Length can be 0, but it can't be negative, all right? But if it's a square, it's not going to have a length of 0. So anything, whenever, let's say length, okay? So if the length has to be between 0 and, let's say this. Let's say it, write it like this. So L length is greater than 0, okay? So anytime the length of the side of the square is less than 0, it does not make sense, okay? And it's impossible, okay? So that's what's wrong with this one. All right, let's go to the next one. What's wrong with this graph? It says the graph relates the number of students going on a field trip and the cost of the trip. Well, we could see what's wrong with this. Let's look at the inputs. 2 students, 4 students, 6, 8, 10, 12, all the way to 20. All right, so what is the cost of 1 student? $40. The cost of 2 students is 50. Cost of 3 students is 60. Cost of 4 students is 70. The cost of 5 students is 80. Now, it says, what's wrong with this? Well, why does 1 person cost? So 1 student equals $40. 2 students equals $50. 3 students equals $60, right? So basically what we can see if we continue this pattern, 4 students equals $70, as you can see right here, and 5 students equals $80. So we can't necessarily say nothing is wrong. However, notice this y-intercept, okay? This y-intercept is an initial value. So somehow, some way, the cost of this trip starts at $25. We don't know what that 25 represents. That 25 could just be a flat fee for these students to go on this field trip. Let's say we use that $25 to pay the bus driver or something like that. So if there's anything wrong, it might be that, but the cost is the same per person. As the number of students increases, the cost increases by $10, okay? And last but not least, we want to know what's wrong with this. The graph represents Han's height since he was 4 until now when he's 14. All right, so let's look at this. The initial value or vertical intercept is, I'm going to say 3. All right, so At 6 years old, let's go here. At 10 years old, Han was 15 feet. Now, I've heard stories and read stories about people that's that tall, but you ever seen a 15-foot tall person? Okay. And they're saying at 6 years old, he was about 7 feet tall. So 7 feet, 15 feet. Okay. So, well, what's wrong with this? 7 feet tall at 6 years old? That's not normal. Okay, so that would be wrong. The output would be what's wrong. Okay, is not realistic. Okay, so let's say we wanted to make this realistic. If we wanted to make this realistic, the age or the input is realistic. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But in order to make this realistic, we would probably have to, let's change the color. We would probably have to change these output values. Okay, so let's change them. I've never seen a 20-foot human being. I've never seen a 30-foot human being. We're not talking about Marvel and DC movies, right? But let's think about a more realistic height. So let's say we change this 10. Let's say so this is 5. So say, let's say 2. Let's say 4, and let's say 6. Now, it could go higher. We could take it up to maybe 8. But let's say this is more realistic if we make these heights or the output values 2, 4, and 6 feet tall. Okay, a person can be taller than 6 feet, but let's think about this too. Is it possible? Is it realistic if this kid at 14 years old is only 4 feet, a little over 4 feet tall, not 5 feet? Let's say 4'5". Okay, I'm saying 4'6". So 4.5 feet tall. Yeah, that makes sense. I mean, they're really short. But we could also change it to this. Let's do something like this. I didn't mean to make those numbers that, but we can make it realistic by simply changing the outputs. Okay, so let's change this 10, the 20, and the 30. And let's say we're going to change these and we're going to make these, let's make them like, at 4 years old, let's say this. Let's say 2, 3, 4, 5, 6, and 7. This is even more realistic. So at 14 years old, a person being, change that color. At 14 years old, a person being 5'5", in this case, that would be more realistic. Okay. So we want to be able to identify whether the inputs and outputs are realistic. I think this is the last slide in this section, and it is. Okay, so take a look at these. If you see places where I made a mistake and I kind of confused you, stop it, rewind it, go back, and do what you got to do. Remember, like, share, and subscribe. Thank you for watching. I hope this is helpful. And as always, I got the solution to your math problems. Deuces.